All right, time to kick off the next design series. So the next thing I'm going to be working on is a trophy truck, a big one. It's going to be an all-wheel drive, mid-engine, 4-seat trophy truck on 58-inch Mickey Thompson Baja Pro XS tires. It's going to be a monster. I don't imagine this thing being race ready like for Baja, but I imagine, a gigantic trophy truck style family rig with 4 seats and all the latest and greatest design principles and technology. So to start, I'm reusing the same Tall-knuckle design from the Ultra 4 rock bouncer. I ended up reducing this height a little bit because the previous Tall-knuckle design was way taller than it needed to be. So I dropped this mounting point down pretty close to the tire, and then there's still clearance here. So if you look at slow-mo videos of trophy trucks, these tires wobble back and forth a ton as they're going over bumps. So there's tons of clearance here, but vertically, they don't really balloon that much. I also found this really great differential design from ProFormance in Australia. So I'm going to try to use this. I'm going to have to reconfigure the steering so that there's clearance. And then I found a bunch of great stuff on GrabCAD. So the first thing that I found on GrabCAD that I got really excited about was this fabricated diff housing. So this, to my eye, it looks like a Ford 9-inch differential with this billet mounting plate and then sheet metal fabricated housing. And this is exactly what the trophy truck guys run. So I was super happy to find this on GrabCAD, and that's what I'm going to be basing the rear axle design on. So traditionally trophy trucks have solid rear axle, and that's what I'm going to be working on first. You can see sort of the finished product here. That's what this video will be going over, and the design principles going into it. The other really great model I found on GrabCAD was this full LS engine. This is a supercharged LS, and this is just one of the highest resolution models I've ever found on GrabCAD, especially for engines. It even has all the rotating components on the inside, like the piston and the crankshaft. So it's kind of a heavy file, but it's a great starting point for the design. And then I also found this 4L60E automatic transmission. I know a lot of the trophy truck guys will run a 4L80E or a Turbo 400 or something completely custom, but they're all pretty much the same size and shape. So this is a great mock-up, and it has the proper mounting features in there. It even has a cutout for the starter motor, which is really nice. Then I'm using an Atlas transfer case to get the power from the front to the rear, and I have an offset drive shaft input to clear the engine. I'm gonna have to move this alternator, but this is probably one of the most accurate drivetrains I've ever started with in a design. So I'm really excited to see how this takes shape. So you can sort of imagine the shape of the trophy truck from here. I'll do a crude drawing in paint so you can see what this looks like. So you can imagine the bottom of the chassis will be here. There's lots of clearance since I'm running portals on the front and the rear. So there's 6 inches of drop from the axle input to the axle output. So tons of clearance, and the seats are a lot more upright than they were in the previous design. So I can have a traditional truck cab, and that will look something like this with a bed, nice A, B, and C pillars, and a hood. So even though it's a mid-engine, the proportions do look like a crew cab truck. So it's not going to look like a 2-door extended cab pre-runner with a really short wheelbase. This wheelbase is going to be pretty long, but the suspension is going to make up for that long wheelbase, and the big tires are driving that so that the proportions are correct. And I think this thing's going to look really crazy when it's finished. I really want to have full bodywork with fenders over the wheels and make it look like a proper trophy truck when it's done. And the other thing is I'm running 2 spare tires in the back so that I can keep the center of gravity as rearward as possible. So I can keep the instant center behind the pivot point of the trailing arm so that this thing's just going to bounce over the whoops buttery smooth. One thing I am going to have to keep my eye on is weight. This assembly is already 4,000 pounds without any tube work or suspension, so I need to make sure it doesn't get too gnarly. So let's jump into the time lapse and we'll talk about the solid axle design. So the first thing I needed to start with was the rear axle. So I'm doing a solid axle configuration on this design, and I still want to run portal hubs. So I'm going to be taking the portal hub shell design with the unit bearing from the previous iteration and copying that over to the rear solid axle. But I need to modify the housing because I don't need a tall knuckle on the rear. I just need an adapter to connect the portal hub to the solid axle. So I need to capture the dimensions for the gearing and then copy that over onto a new back faceplate for the portal hub. So if you remember, I have the output drive, the input drive, and then 2 idler gears. And this part of the portal hub reduces the gear ratio at the wheel by a factor of 2. So since I'm running the 58s again on this design. I want to keep that gear reduction in the front and the rear, but just with a solid axle configuration. So the first thing I need to do for this rear backing plate is make all of the features for the bearings and the gears so they can interface properly with the outer portal shell and capture those drive gears. So I'm just copying those dimensions over from the previous design onto this simple back plate. So now I'm dropping in that back plate to the assembly, and then I can start figuring out how to adapt it to the solid axle. Now I'm dropping all the gears in and making sure that all the mates are proper to keep the gears and bearings constrained but still able to rotate. And it looks like everything is correct there. Then adding a light weighting cut to this part and some chamfers. So now I'm dropping that portal hub into the rear solid axle assembly, and the differential housing is offset from the center by 12 inches. So I'm trying to find a design reference for a portal hub on a solid axle. So I started with 74 weld, and they make Jeep portals for the steering side, but I needed to find an example for the rear axle. So I found this example from Curry, and Curry has a really unique way of mounting their portal hubs to the axle. They basically have a big boss, a machined boss on the axle housing, and then that bolts into the portal hub. So that's the first design I'm going to attempt. So I just need to make an axle housing tube, which was a 3.5 inch inside diameter with 1/8 inch wall thickness. And I'm doing the short side first. Then I have a big square boss here, but I need to find some hardware that's going to interface with it and make sure there's enough clearance. So I ended up going with these grade 8 1/2 inch flanged bolts, and those are great because you don't have to use washers, so it reduces hardware, and you still have a lot of material to interface with. And I figured this boss would just be a big piece of billet 4130, and then you could weld that to the tube, which is also 4130, and then adding that mate, and then mating the portal hub to that, and then I'm going to try to put some bolts in there. So I sort of ended up barking up the wrong tree with this design for how to interface it, because I figured what would be best would be to embed some lock nuts on the inside of the portal box and then have bolts come in from the outside to capture everything. So you can epoxy in those lock nuts on the inside so that oil doesn't get through, and so that they stay fixed in place as you take the bolts in and out. That way you don't have to take the whole portal box apart to disassemble it. You can just run those bolts out through the back and take the portal hub off of the axle. But as you'll see here in a minute, the design ended up not looking like it was strong enough in all 3 axes. It really was only constrained rotationally. And so this design is just playing around with different bolt configurations and distances. So now I'm trying rotating those bolts, but I have some interference issues with some pre-existing bolt locations. So this wasn't quite going to work either. Now I'm realizing that the O-ring groove for the sealant on the portal shell is going to be right on top of one of those lock nut locations, so that's not quite going to work either. This is part of the iterative design process. Is as the design develops, it's sort of, I heard a mechanical engineer say that once you start, the design reveals itself to you. So once you set your constraints and your envelopes and what the part needs to do in terms of features, then you can sort of visualize what needs to happen next at every step. So the next thing I'm going to try is to put the boss on the backside of that plate, the portal hub backing plate. That way it can be made out of aluminum. It's easier to machine than 4130 chromoly is, and I can offset those bolts. So I can get the bolts out of the inside of the part and put them on the exterior of the part. And this ended up being sort of the right concept, but still had interference issues. So what I'm going to try is some threaded inserts and embed those. Those can be epoxied in as well, but I still had the interference issue with the O-ring on the inside. So the way this design is configured right now, oil would definitely leak out of it. So I didn't ultimately end up going with this exact design, but I used the same concept for the final design for how to attach the portal hub to the solid axle housing. And I wanted to increase the mounting strength rotationally by adding that extra bolt down at the bottom, because you figure this part of the hub is kind of a moment arm between the wheel and the axle, and so it's going to see the biggest force not just vertically as the wheel cycles up and down, but also rotationally as the drive torque rotates the wheel about that moment arm and that offset from the portal draw. So this is starting to look pretty good, but I still have that interference issue with the O-ring. So the next thing I'm going to try a different version of this design with way more bolts, more spread out, way wider, adding some more mounting bolts here in that rotational pattern, which ended up being kind of a funny shape because they're not all on the same radius with respect to each other. So it looks a little wonky, but it's starting to look like it's getting there in terms of strength. So now I just need to copy that pattern over to the backing plate on the axle housing so that it will mount up properly and have all the bolt holes in the right location. So now I decided maybe I'll just flip the bolts in the other way. So the bolts are embedded in the portal box with epoxy so that no oil can leak through, and then you just have the nuts on the outside. So this will definitely make it a lot easier to assemble, and it's starting to look like we're headed in the right direction. So now I'm going to copy that over to the other side of the axle. And again, since the differential is offset, since we're in a mid-engine configuration, the other side of the axle tube needs to be way longer. So that's going to be an important consideration when I do the bracing on this part. So I just copy that part over, save it as a new part, and then increase the length, and then all those features over all those bolts. So now I'm starting to think about what type of bracing I need to add for the housing. So I'm looking at some Ultra 4 rear axles that have the offset diff and some trophy truck rear axles to see what kind of 4130 sheet metal fabrication they use for bracing, because you don't want just a straight tube. You want to add rigidity in all three axes, and a tube is the strongest shape in torsion, but it's not the strongest shape in bending. So I need to add some sheet metal bracing. So the first thing I'm going to do is add the 4-link mount to the top, which is going to be centered right on top of the diff. So I need to go back to the old design, copy over the spherical bearing rod ends and see what size they are, because I want to reuse that hardware. And so I need 5 inches of diameter clearance for that spherical bearing rod end with a 9-inch offset from the center of the diff to the 4-link mount. And this is going to be a totally different suspension configuration to what we had previously in the Ultra 4 design. That was an independent suspension design. This one's going to be a traditional solid axle trophy truck design, sometimes called live axle. So you have a rear solid axle that's bouncing up and down, and you have a triangulated 4-link constraining it with big trailing arms and 4-link mounts on the top. So this is that first mounting bracket that's going to go on top of the diff and capture that top rod end. And I'm inserting this as a sheet metal part in the assembly. And then during fabrication, all of this would be welded together. So you would cut these pieces of sheet metal out and then weld them to the diff assembly. And then adding in the hardware here for that spherical bearing, the misalignment spacers, and that big giant bolt. Then adding some bracing here to box that in. So this is a really simple part. It's just flat sheet metal with no strange cuts. And then I'm just boxing it in so that it's rigid. Then I need to add one for the other rod end mount. This one's not going to be on top of the diff. It's going to interface with the tube of the solid axle. So this can be a simple slot shape with boxed bracing. And then this would be slipped over the tube and then welded in place at a set distance. Then I just need to copy that hardware over, and it's starting to take shape. So then I'm just going to flip this upside down for the trailing arm mounts, because the trailing arm rear mount diameter is the same as the rod end, but it doesn't have to have that big offset. And I want this mount as close as possible to the tire so that I can have maximum ground clearance. And then you can imagine where those trailing arms go on the outside. And then the 4-link mounts go on the inside. Same hardware copied over. So the advantage to this design working from the Ultra 4 is that I had already picked out all the hardware. So I'm confident that I can reuse that everywhere, and it's going to be exactly what I need. And it's starting to look pretty good. So I want to add some more bolts here and make the mount as wide as possible, but still have some lightweighting cuts in there. And so that's what I'm working on here. Chasing around some broken fillets and radiuses. So then I figured what I would do is I would just add a sheet metal extrusion here to connect the portal hub to the trailing arm mount with those big cylindrical extrusions. But I didn't end up liking the way that this looked. It looked kind of boxy and bulky, and I was worried about ground clearance. And the main issue with this version of the design is that there's no way to access those bolts on the inside unless you cut in a window, which would completely compromise the structure. So I ended up abandoning this design and going to something completely different for how to tie the portal hubs to the solid axle. So I thought maybe if I angle those vertical walls, I can access more of the bolts, but I'm still missing one of the bolts and I don't have access to. So I ended up sleeping on this design. And what I decided was, rather than use sheet metal to tie everything together, I'm just going to extrude the portal hub backing plate out with a big billet flange and get it as close as possible to that 4-link mount and bolt everything through there, because it's a lot easier to make billet than it is to do a bunch of complicated sheet metal fabrication. And then I can add these little heat treated inserts embedded in the aluminum to tie everything together. So first I need to reduce that bolt size on the trailing arm mount. It's about 1 inch too long. So I'm going to swap that out from McMaster using a shorter bolt so that I have more clearance. So I'm going to start with an offset plane to get it as close as possible to the 4-link mount. Then I'm going to make a base flange, which is that circle that you're seeing. And this is going to be the main mounting interface that I will embed those heat treated inserts in, and then I can add the bolts in. And then I can tie this flange to the main backing plate for the portal and arrange it in a way where there's lots of clearance for assembly. And so there's two main advantages to this design. You still retain your rotational strength, but your vertical load is now captured by that billet boss that we're looking at, that big long cylindrical tube, which ended up being 9 inches long. So the chromoly tube on the solid axle will insert into that cylinder and will be the main load bearing vertically. And then all I have to do is constrain it rotationally, and it's way stronger than the previous design. And this part is totally machinable with those pocket cutouts. But the next thing I need to do is add some pinholes. So one important thing for assembly design, when you're bolting two parts together, the bolts are only strong along their axis. So like along the length of the bolt is the strength. Whenever you put a shear load on a bolt, it's not as strong. So whenever you have a rotational force between two parts, the way to constrain that rotationally and retain shear strength is to use pins, because pins shear strength is way stronger than bolts shear strength. And so that's just sort of a best practice in mechanical engineering, not only to register the parts together so that they're really precise, but to constrain any rotational movement that will induce a shear load on the bolts. So now those bolts' only job is to tie everything together face to face, and then the pins take care of the rotational strength because they have way more shear force that can be imparted on them before they break. So I'm using 1/2-inch pins here. Another best practice for pins is you want to use a press fit in the aluminum and then a slip fit on the other part. And a good rule of thumb is whatever the diameter of the pin is, you want double that diameter to be cut into the part that the pins are going to be pressed into. So like, for example, I'm using a 1/2-inch pin, 1/2-inch diameter pin here, and I'm going to embed them 1 inch into the aluminum press fit, and then they're going to be sticking out a 1/2 inch into the chromoly 4130 part that they're going to be slipping in and out of. And the reason you do that is if your pins aren't pressed in far enough, they're likely to have an angle to them, and then you'll have a really hard time assembling it. And I really like the way this part ended up looking. The hardware configuration was a lot simpler, the machining is a lot simpler, and the strength is all there. So now I can just add those bolts in and the pins and do one pattern to rotate them around, and this assembly is starting to take shape. So now the next thing I'm going to work on is the bracing. And there's a really common configuration that a lot of the trophy truck builders use, where they use a bent piece of sheet metal that's cut out and sort of wraps around the axle and ties all of the mounting points together to the diff, the 4-link mounts, and the trailing arm mounts. So I need to make sort of a complicated sketch here so that I can get all the dimensions correct for the cutouts for the diff, because they're all at weird angles. And I want the bend to be at an angle with respect to the axis of the tube. So I need to create an angle plane that I'm going to be generating the boss from. And I'm doing that with a 3D sketch here so that I can generate a plane and then make that sheet metal bend around that angle. So I'm just doing a boss out that direction, and then I'm going to make a cut that represents the tube. And this part looks really great. It ties everything together. It's very sleek. There's lots of clearance and there's lots of strength because of that bend in the sheet metal. This is way better than boxing it because you use one piece of material and you don't have to rely on the strength of your welds along a really long line. You can just take one flat piece of sheet metal, bend it, and then weld it right on. So then I'm going to do the same thing on the bottom, on this long side of the axle, and then I just need to modify some of those cutouts because the diff has a different shape on the bottom than it does on the top. So then I just need to copy this part over to the other side and make it shorter, and I can keep those same cutouts, and it's going to look great. Same thing on the bottom, and this part is starting to look really rigid and really nice. So again, the reason I'm adding these bracings on the tube is because I want to add rigidity in the vertical direction of the solid axle and the horizontal direction of the solid axle. And so these braces tie the tube into the diff in a way where it's proportionally rigid and it'll take crazy shock loads as the live axle bounces up and down over the bumps. Then I need to figure out how to tie these two 4-link mounts together. And I figure just a nice sheet metal extrusion here is probably the right way to do it, but I ultimately ended up going with something different because I couldn't access the bolts again. And also, this is a giant wind trap, and I didn't want that much wind resistance on the axle. So I'm going to make another brace here that ties in the 4-link mount to the trailing arm mount. And it's the same thing. It's a bent piece of sheet metal at an angle and then cut out around everything. So that's that triangle shape that you're seeing here. Then I need to make a 3D sketch so I can define that angle plane. then I can start drawing the shape of the sheet metal. Now I have that shape. I can extrude that out to the plane and then start making the cutouts. So the first circular cutout is for the axle tube housing, and this is going to brace the forelink to the trailing arm. Then I just need one more cutout vertically right here to tie everything together. And there's plenty of room to access those bolts, and there's tons of rigidity on the part. So I figured to tie the two forelink mounts to each other, I would just do the same type of bent sheet metal, but at an angle, so that there's plenty of room for the hardware and it's not as much of a wind trap as it was before. And then I can just cut around that diff. And this part looks a lot simpler, cleaner, and stronger. And there's different cutouts on the front and back because the front face of the diff is flat and the rear face of the diff is sort of an octagon shape. And then all these parts interface with each other really nicely. And then I can copy that angled piece over to the other side and then just add some extra cutouts for the diff. And that's what these cuts are here. So SOLIDWORKS has this really cool sheet metal tool. And what you can do is you can take a part that you've made using traditional modeling. You can convert it to sheet metal by selecting a base flange and collecting all the bends automatically. And then there's a feature called flatten. So you can take a sheet metal part, flatten it, and then you have your cutout for what bends you need to make.